This is a follow-up to my first video where I detailed the Lewis structure for the molecule from the Guide to Lewis Structures. I'll be going over the second molecule here in a bit more detail, since that one was a bit more curtailed in the guide as it was given. So for this one, we're going to be working with another familiar molecule. This one is O2, the oxygen in the air we breathe. And we're going to go again through the process from start to finish so that we can see how this one plays out, because there are a couple of differences between this and the last one. The first difference becomes clear right in the first step. Our first step before was finding the central atom, but in this case we only have two atoms to deal with. In a case where we only have two atoms, there's no real point in finding the central atom because each of the atoms is going to be bonded to the other one, and there's not one single atom bonded to all of the remaining atoms. So because of that, we don't need to worry so much about this. We can just go ahead and write out our two oxygen atoms here. And that will be a good skeleton framework for what we do going forward. From there, we're going to follow a lot of the same steps, where we again have to find the valence electrons. In this case, though, we're only going to be dealing with one element. We're dealing with oxygen. And from the periodic table, we see that it has 6 valence electrons, member of group 16, and we could justify this using our electron configuration knowledge, but it'd also be good to start getting used to working with the periodic table and recognizing the number of electrons or number of valence electrons from the group in which it appears. We can see from the formula that there are 2 atoms of oxygen, so we should multiply that 6 by 2, which gives us 12, and that's our total number of valence electrons in this case, since we don't have any other atoms present. We'll go ahead and start adding these to the structure in the same way that we did before by drawing in single bonds to connect the elements together. In this case, though, we only draw on one single bond because there are only 2 atoms to connect together here. Because that line represents 2 electrons, we have used 2 out of our 12, leaving us with 10 more. Again, in this case, we don't need to worry so much about which atom we start with going forward because we only have atoms of one element. So as we start to add the rest of the electrons as lone pairs, we can just pick one atom and fill it up. So I could pick this left oxygen atom. I can see that it already has 2 electrons from that single bond to it, meaning it needs 6 more. So I'll add those as lone pairs. I want to do the same to the other oxygen atom, but I should be mindful of how many electrons I have remaining. Just to keep track of this off to the side, I can go ahead and subtract the 6 that I added, meaning I only have 4 left. So I'll go ahead and add those to the other oxygen, and again I've reached a point where I have run out of electrons. Once we run out of electrons, we need to do our double check process to make sure that we have gone and completed this. So, counting up the total electrons, I do see that I have a total of 2, 4, 6, 8, 10, 12 electrons. So that passes my first check of total number of valence electrons. Then I will check for my octets. I already checked the left one, but I can do that again by looking at this oxygen, which has a bond. It's 2 electrons, 4, 6, 8, counting the lone pairs, so that one is fine. When I look at the right oxygen, though, I see I only have the bond and 2 lone pairs on there, which brings me to a total of 6. It does not have the octet it needs, so it does not pass my double check. What that means is I'm going to have to take some additional steps here to make sure that we can get all atoms to a stable state while using the correct number of electrons. As I mentioned in the previous video, what that's going to mean for us is moving the electrons around on the structure. We can't add any more or take any away. We just have to deal with what we have. The way that we get up to octets on all of the atoms is by sharing more of the electrons. What this means is that instead of having just single bonds, one pair of shared electrons between each pair of atoms, we may have to do double or triple bonds, cases in which we have 2 pairs or 3 pairs of shared electrons between the atoms. If I focus on the oxygen on the right, I see that it is short 2 electrons from what it needs. It had a total of 6 when we counted, but it needs 8 for its octet. We'll get there by sharing one of the left oxygen's lone pairs. I can focus in on this one up here and say that it's going to share that lone pair with the other oxygen. When I redraw this, it's going to look a bit more like this. So this accounts for the lone pairs that remain on each atom. Each atom has 2 lone pairs on it. And because I used that other lone pair, the one that's circled in red, to make another shared pair between the oxygens, I'm going to draw that as another covalent bond. So that double line there represents our double bond, each line being a shared pair. So now there are a total of 4 electrons shared between the 2 oxygen atoms. Let's go through our double check at this point to see how we fare. If I count up, I have a total of 2, 4, 6, 8, 10, 12 electrons on the structure still. I didn't add any or take any away, so that check still passes. Let's see what happens with the octets now. If I look at the left oxygen, it has 2, 4 electrons from its lone pairs, and then an additional 2, 4 from the bonds. That brings us up to a total of 8, which is good. The right oxygen looks very similar. It's got 2, 4 from its lone pairs, and then also 4 from the 2 shared pairs in the center there. And so that means that it has an octet as well. All of the atoms have passed our double check, and so it means that we have now gotten to a good Lewis structure for the oxygen molecule.